So many thanks for everyone. So very good afternoon. Thank you for staying until the end. So hopefully you find this kind of the presentation is complementary to the previous presentations, because for this one we're going to focus on more kind of system level optimization instead of semiconductor itself. So so the topic is really about the multi-objective optimization for the automotive powertrain. So quick introduction about myself. So my name is Wenlong. So as Alistair mentioned, so I'm a senior research fellow from senior CSA Catapult, but also a senior lecturer from Cardiff University, so with both organizations. So this is kind of the outline of the presentation. So starting from basic introduction, so what we are doing in the CSA Catapult. So if you don't know where we are from or what we are doing, and really the second part, the majority of the slide is going to be dedicated for the technical part, talking about this multi-objective optimization, really. So starting from kind of the where we are, so we start CSA Catapult basically is in South Wales. So we are in Newport, so about 10 miles from Cardiff. And at the moment, I think the recent number I got here, I think we got 96 staff already, but still growing. So we are focusing on basically 3 areas about the photonics, RF, and also power electronics. But we have a state-of-the-art packaging lab as well. I mean, basically working with the 3 teams on these 3 topics. So, and a bit more about vocabulary in the CSA Catapult. So we do focus on the 4 areas. So starting from the modeling, integration, characterization, and also the validation. So if you are looking at partners for project about these 4 areas, I think the best person to speak is not me, it's actually Alistair, who is chairing the session. But yeah, do speak to us if you are interested in any of these areas. So moving back to kind of the technical part of this presentation, really talk about the multi-objective design. So the first question, or the first thing I want to go through, is why we need multi-objective design, because it's not something new. I think probably some of you already are doing this for your previous design with IGBT, for example. And this is kind of the tear down of the Tesla inverter, but that's a previous presentation with IGBT. But now they actually move into the silicon carbide MOSFET. I mean, if you see from the top to the bottom, you got the control board, until the end, you got the DC link capacitor. So 9 components, probably going to be a few more, not really highlighted here. But you see, the point here is you got a lot of components in this inverter. I mean, the semiconductor is just one part of that. So how you make the best use of semiconductor like the silicon carbide MOSFET? I mean, that's a big question we really want to answer through this presentation. And for example, very simple question is you have the silicon carbide MOSFET. I mean, very good performance, but how much is the switching frequency, for example, you should choose? I mean, because it can probably go up to even 500 kilohertz. I mean, go down to probably 20, 30 kilohertz. But what is the optimal switching frequency you should choose? That's kind of the one type of the question. So really want to use this slide to summarize the challenges we are facing. So for a traction inverter, or pretty much any power inverter, so we got the challenging left side. So for example, we got a lot of trade-offs among efficiency, reliability, cost, volume, and they are highly correlated. So one example I just mentioned, for example, when we increase the switching frequency, so we'll shrink the size, for example, the inductor. But the bad thing is that we'll increase the size of the heatsink, for example. So a lot of trade-offs that we actually need to balance. And also the things making it worse is about the cost, because we have a higher cost of the silicon carbide MOSFET at the moment. So we should really think about, I mean, how to make the best of use the good performance of silicon carbide MOSFET to shrink the size of the other components, so we can save the cost from the other components. So in the end, hopefully we will have actually lower cost compared to IGBT-based solution. So kind of the strategy or the solutions we want to talk about here is a multi-objective design. So the biggest challenge is how we can accurately and fastly map a relationship between the design space and the performance space. So the design space I'm talking about, for example, your topology, what kind of semiconductor you're using, and what kind of inductors you're using. So that's called kind of the design space. And then performance space, we are talking about the, for example, your efficiency, different switching frequencies with different topologies, and how about your reliability across the life cycle of the traction inverter. So all sorts of questions. So we need to find a way how to build actually a relationship between the design space and the performance space in a very accurate but also fast way. So that's kind of the challenge we actually are facing, because we got so many components, highly correlated, and considering the silicon carbide MOSFET, the switching speed is so fast, we're talking about less than 100 nanoseconds. So that's why makes things actually even more challenging when we change from IGBT to silicon carbide MOSFET. So here is kind of the solution we are actually developing. So we from the left side to the right side. So we divide the kind of the solution into 4 steps. So we start from the characterization, then do the modeling, and then do the optimization, and finally we do the verification to check, for example, whether our optimization results match with our prototyping. So so here we actually pretty much kind of stays true for almost all polishing converters. So for the rest of the slides, so I'll quickly introduce each step, step 1 to step 4. But going to use silicon carbide MOSFET as one example, for example, the characterization, the modeling, optimization, verification. And eventually I'll present the case study. It's going to be the battery charger. And, silicon carbide MOSFET is not only thing we need to characterize and model. Unfortunately for this study, the other thing is about the inductor, capacitor, actually I would say equally important. So, I mean, let's start from the characterization. I mean, characterization is not a topic new. I think several colleagues in the previous presentation talk about how to do the characterization. And here, so what I want to focus is really the challenges we are facing to do the characterization in a fast, accurate way. And so the problem we are facing is actually the switch much faster. I mean, and also we have actually need to look after, for example, the characterization at a different temperature. And the other challenging thing is about the speed. So after we do the characterization, then we need to think about how to model that. I mean, the model itself actually is quite challenging because we need to talk about the speed and also the accuracy. For example, if I mean, we need to build a model not only for one silicon carbide MOSFET module, but we are talking about probably quite a lot of them in one system. For example, you got parallel of them, like what Tesla is doing. So here, the method we are using is the artificial neural network. So what we do is we do the characterization, but not only in the low IV region. We actually characterize the performance of the silicon carbide MOSFET also in the high IV region. That's actually what happened when the device is on and off. I'm talking about that 100 nanosecond, what happened. So then we use this actually data to do the to feed into the artificial neural network. So what we did for that part is we need to look after, for example, the layers or the structure of the artificial neural network. And the other thing we need to think about is the convergence of the final model, because we use that model to do the simulation. So we need to make sure that the circuit model can be converged. So that is a thing kind of the challenging we face, and this is some preliminary results. And we actually test our characterization and modeling results based on artificial neural networks. So what you found is, so the error of the IV curve during the, this is the off process, the relatively IMS error is actually less than 3%. So we compare this performance from some commercial software, like some software from Keysight to do the modeling characterization. So we found their error is around probably 15, even 20%, but we significantly reduced the error during the on and off. And in terms of the speed, so we actually improve the speed of simulation more than 50%. So you'll find more details in this recently published paper. So because of the limited time, didn't put all the results here, but if you have any interest, so do feel free to have a look at paper. It's open access, so everyone can download it for free. So that is about really the step 2. So moving to the step 3, as I mentioned. So we are not optimize the whole inverter in one point, but we are talking about tens of thousand points, the mission profile, so that kind of stuff. Then we need to, basically what the basic thing or the most traditional thing, we can do a grid search, which means that we go through all the point, all the mission profiles, and then calculate the efficiency, the power density, the reliability, for example, and then make a decision. So how we should, for example, how big the inductor or how big the capacitor should be. But that is very time consuming, so we actually made a calculation for a grid-tied inverter before. So we found if we are doing this, then pretty much it's going to take several months' time, considering yearly profile, mission profile. So that's definitely not acceptable. And so the other candidate programming language are geometric programming or partial swarm or generic or moving to the artificial intelligence. We actually compare these different programming language, optimization algorithm, and so what we end up with is this process, and based on artificial neural network. So we found that is the fastest and the most accurate way to do this optimization. So we actually will start from the left top side, and we got the results from the modeling, and then modeling results will feed into this optimization algorithm, and then we use this either simulation or mathematical model depending on how complex your circuit is. So we have 2 different rules. So you can use, for example, Plex simulation to generate your power loss data, but you can also rely on the mathematical model. I mean, depending on what kind of circuit you want to optimize. So after that, we will actually generate, if you see the bottom side, we got some training data, and then going to be fed into the artificial neural network. So we'll use that training data we generated either from mathematical model or from the simulation to actually run through the mission profile. And then we will find the Pareto front, we call it, but actually it's the optimal performance of the inverter. I'll show you what it really look like in the next slide. But after that, so we actually build an internal database to calculate the cost and also the volume, that kind of stuff. So, and eventually we'll got the optimized design for EV inverter. So here is the kind of the verification we have done. At the moment, we use this single-phase battery charger actually to verify what we presented, because this is one of the most popular and also simple kind of the converter we're using now. So the results, I think, looks very promising. So if you have a look at the left side, top one, the table, so we are doing a 1 kilowatt battery charger. So we have the design performance and also the testing performance. So for both efficiency and the power density, you see they are quite close to each other. So the error is pretty low, below 4%. So that's verify our design methodology actually. So this is what the prototype looked like, basically. And that's the top side. So if the bottom side, a bit more results about what we are talking about. So, here we mean this is the Pareto front. Actually, is an optimal design you can choose. Again, it's a trade-off. I mean, when you increase efficiency, you actually got lower power density. So that's kind of the trade-off. So in terms of the computation time, we actually compare performance of the different optimization algorithm. So as I mentioned, we can rely on numerical model. That is the most traditional one, and also more advanced one like geometric programming. But at the moment, we're using artificial neural network. So what we found is, so the artificial neural network actually have the least computational time, which means that you can design your system in a much faster way. So that is what we found. So a quick summary about what we developed. So this is obviously the starting point of the story, because you see we haven't actually applied this one to the motor drive design, which is pretty much our focus, and also the next step. So, we are doing this through this AESIN project. So it's an end-to-end supply chain development for the automotive power electronics. And pretty much, I mean, CSA Catapult, so we are doing the market side, also the evaluation, but also the optimization and the packaging side. So that is about the end of the presentation. Any questions? Really? Thank you.